First of all, thank you for the invitation to speak here today, and thank you all for coming. Contrary to what the picture may suggest, this is not a talk on geology. Azurite is, as we'll see, is a new algorithm for finding bases of loop integrals, and this is work that has been published in two papers with my collaborators, Alessandro Georgoudis, who's a student in Uppsala, and my colleague at ETH, where I did my previous postdoc, Yang Zhang. So this is a little bit of a technical subject. So I hope that I will manage to explain, the topic in a way that's still comprehensible. But let me start by giving some kind of overview of what is the okay. Our starting point is this basic statement that if we consider basically any object in perturbative quantum field theory, for example, a scattering amplitude computed in some fixed loop order, this can be expanded in a finite basis of integrals. So there's an algebraic proof of this relating as a special case of something called Bernstein's theorem, the theory of D modules, if you're familiar with that, in this paper here from 2011. Again, this proof is algebraic, and it proves that the number that's a finite basis, but it doesn't give you a specific number or way of finding such a basis in practice. But this is somehow the basic statement, and what we're after is to be able to, if we choose some object here on the left-hand side, could be a 2-loop amplitude, 3-loop amplitude, or a correlation function, or whatever. What we're interested in what this algorithm will produce for us is some choice of basis of the vector space that's relevant to express this object.
I have a question.
All right.
So, is it just obvious that there's a finite basis? If you're doing a perturbative expansion of
yeah.
fields, and by definition, I mean, unless you have an infinite number of nonlinear interactions, there's no way to.
So one thing, I mean, which makes it non-obvious is if you just write a Feynman diagram which has some propagators, you can consider taking arbitrary integer powers of those propagators, and that already gives you infinitely many integrals. On the other hand, you have infinitely many linear relations, and we'll see, what these are. But it's not obvious that.
It's not just sort of a finite number of contractions of.
No,
there's always a finite number of contractions or sort of propagator building blocks.
This is true. But I mean, for example, just by considering the powers of the propagators, there really is a priori and well, there is an infinite dimensional vector space. But on the other hand, there is an infinite number of linear relations. So it's not obvious how how this plays out, basically. But it has been proven. I mean, again, relating to some theorem, that the number is always finite. Yes.
Any idea on how M scales with L, behaves in L?
It depends very much on multiplicity as well. So it's not really no. This is still very much an open question. But I can say that this reduction here is a very significant reduction. It becomes increasingly dramatic as you go to higher loop orders and then higher multiplicities. And I'll give you two examples in 1 or 2 slides from now. But as for this number, I mean, I know of a separate way of computing this number, but that is also not. I mean, this has to do with looking at the parametric representation of a given integral, and then you basically look at critical points and you associate so-called Milnor invariant to these critical points, and then you add these, and this will give you the number of master integrals. But again, one has to do a computation for each specific case. There isn't a sort of a closed formula. Okay. Now, I mean, this is a problem which occurs many places in perturbative quantum field theory. So people thought about it for a long time, and of course there are some standard approaches for finding these reductions and for finding these master integrals. And what I think most people would agree is sort of the standard approach was written down in 2 papers by Laporta in in 2000, and basically the idea is that you write down all the possible, first of all the possible integrals that are relevant to express this object from the Feynman rules, and then you enumerate all the linear relations, and in the next coming slides I will try to explain what are these kind of linear relations that are relevant. But once you've enumerated what you think anyway are all the linear relations, then you will have a large system of linear equations that you can then, in principle, apply Gauss-Jordan elimination to. And the only problem with this in principle works in general. The only problem is that these kind of linear systems that we're talking about here are large linear systems. I mean, they can involve millions or hundreds of millions of equations very easily. So to actually perform this step of Gauss-Jordan elimination, basically you try and run it first on your laptop, and then it runs out of memory. Then you reserve some time slot on some computer cluster, and you find that this also runs out of memory. I mean, so to actually do this at some point when the complexity becomes high enough, you need new methods. And so that's the motivation for why we started to look into this. And in our code Azurite, the basic idea is to use unitarity cuts to try and block diagonalize these systems of linear equations. So the standard approach tries to do Gauss-Jordan elimination on large systems like this, and what we'll see what will happen in our approach is that by use of unitarity cuts, you can basically divide this problem into several smaller subproblems that you can more easily manage to solve. Okay, don't worry if any of you are not familiar with what this unitarity cuts means here. I mean, I will try to explain this as well. Okay, but first let me take a step back and explain. So I said that what we need to know to proceed in this problem are all the linear relations that exist between the loop integrals in our problem. Two kinds of relations. One of them is discrete symmetries, which I think is just familiar from standard quantum field theory, Peskin-Schroeder, something like that. The other kind of relations that I expect would be perhaps less familiar are what's known as integration by parts identities. So let me say a little bit about what these are. So basically, I've tried to write schematically what these kind of relations are here. So this is some integrand of some completely general L-loop Feynman diagram. D1 through dk denote the propagators that can be raised to some positive integer powers here. And in the numerator, we may have some polynomials in the loop momentum and the external momentum, along with what's technically called IPP generating vectors, which are also polynomials in the loop momentum and the external momentum. And now the observation is basically Stokes' theorem. If I take total derivatives and I integrate this object, these total derivatives in d dimensions, I get a 0 in dimensional regularization. So this might seem like a pretty innocuous statement, but once you try and, for any given relation, write out the action of these differential operators on the integrands, you find that they relate a number of integrals with different topologies, and in fact there's many linearly independent relations of this kind. In the next slide, I think I have some examples of just how many. I mean, there are in some practical cases. Suffice it to say, for now, it's a very powerful tool. Here, let me just give you an example of what these relations could look like in practice. So here, all the internal and external lines are massless, and then S is just the usual Mandelstam invariant K1 plus K2 squared. Chi means T over S. And then you have, for example, you have a relation like this. I should explain the notation here as well. This dotted line here means that you multiply the integrand by this object, which is so the dotted line means that you take the dot product of the momenta adjacent to the black dot. So this external momentum here dotted with this loop momentum here, and then that object squared is multiplied into the usual integrands, I mean the product of propagators, to form this integral. And as it turns out, we have a relation that tells us that this integral can be expressed as a linear combination of these integrals on the right-hand side. So this is a special case of this kind of decomposition here, applied to just a single integral. And the coefficients here they're always going to be rational in the space-time dimension and the kinematical invariance. Okay, so this is what one such relation looks like, in practice. Okay, say a little bit more about the role played by these integration by parts identities. So they're very important if you're trying to do a fixed order calculation in perturbative quantum field theory. Say you're computing a two-loop amplitude in QCD, something like that. Then actually in practice, these IBP reductions form the bulk part of the calculation. And they, in that context, play two different roles. So one is that of reduction. If you think about computing a two-loop amplitude, first, if you enumerate all the possible Feynman integrals, there will be will be a very large number of contributing integrals, and the first role of these identities is to allow us to reduce these integrals down to a basis, which in practice is much smaller. So here's some numbers to give you an idea. If we consider just the 4-gluon amplitude in QCD two loops, this allows us these reductions allow us to reduce something on the order of about 400 integrals down to a basis of 13. If we consider in QCD gluon fusion from Higgs production from gluon fusion at next to next leading order in alpha S, the reduction is something like from 500 million Feynman integrals down to about 1,000. So this reduction is very significant, and it grows ever more significant as you increase the complexity of the problem. So this is one role. I mean, so IBP reductions allow us to reduce this huge number of contributing integrals down to a much more manageable size of integrals, a basis of integrals that we then have to deal with. But moreover, they also allow us to compute this basis of integrals themselves. In that they allow us to set up differential equations that are satisfied by this basis of integrals. So it's to see how this works. If you pick any one integral ij in your basis, and I'll pick some external kinematical invariant, some Mandelstam invariant, for example S or T, and differentiate ij with respect to that invariant. The results can be again written as a linear combination of the integrals in the basis, simply because it is a basis of the vector space that we're looking at. But to actually do this rewriting in practice, one has to use one uses these IBP reductions. So to actually find what that decomposition looks like in the basis, you really need to have these IBP reductions available. But once you do have that, then for this integral ij, you get one differential equation applied to the full set of your basis integrals. This allows you to set up this first order linear system of linear equations satisfied by your basis integrals, and then assuming you can also find boundary conditions satisfied by the basis integrals, you can use these differential equations to compute this basis of integrals. And should say here that beyond one loop, this is actually the way that people really compute these basis integrals. So yes, there was a question.
So yeah, if you have like generic initial conditions, like some generic linear power spectrum that you're computing loops around, do these integration by parts tricks work? Because I would imagine you would like hit the power spec, the initial conditions with a derivative if you try to do. You see what I'm saying?
Well, but I mean so you would use the integration by parts reductions for the full integrals, right? But for the boundary terms, I mean, then that's just some additional. I mean, it's just to find a unique solution for your differential equation. I guess I'm not fully understanding the question.
Yeah, I guess so. The one loop integral will be integral of d3k times some kernel, which depends on the external momenta k external and the internal one k of some initial conditions p linear of k. Sometimes it's just, I mean, in QFT, I guess it's always you're in the vacuum or something, but if you're just perturbatively solving, for instance, in cosmology, we have the initial power spectrum from inflation or from depending on what we're doing. It's some function of k that we integrate this kernels over the nonlinear kernels. Now, if I tried to do an integration by parts, I would imagine I would get a derivative of my initial conditions.
But you're not applying integration by parts to your boundary value problem, right? So I mean, it's really you use the integration by parts reductions to set up these differential equations, and then and to find the boundary value of your integrals. That's a separate problem.
No, I guess so.
Right.
Maybe I don't understand this procedure then. So my impression was, if you write some big loop integral, you've got a bunch of just a lot of terms which naively look separate, but some of them are related by integration by parts. So if I did a bunch of integrations by parts by hand, I could reduce this set of 1,400 integrals down to just 13.
Yeah.
And I get, okay. Is that right, or?
Yeah.
Okay.
I mean, indeed, and so these 13 or 1,000 are the integrals that would appear here. I mean, and again, I mean, the IPP reductions are really just used to set up these differential equations. I mean, after that, in some sense, that the role of these are played, and you have to find separate methods. I mean, where you don't apply IPP reductions to find the boundary values of the integrals. So it's a separate problem. It's a very non-trivial problem as well. So I should. But I mean, there are different ways of solving them. In one way, you can basically, if you can find the right choice of basis, you can trivialize solving these equations to find the boundary values of the integrals. Is then more non-trivial. This is a paper by Johannes Henn. I don't know if you. There's a different approach where you introduce some auxiliary parameter, and then it becomes harder to solve the equations. But in practice, the boundary values are almost always 0. And you can just use numerics to fix them basically, but practically for all the basis integrals in that scheme, I mean, then they will be 0. But I mean, okay, I can add it. It's a non-trivial problem in general to find the boundary values. Okay. Anyway, just to summarize, I mean, so if you're attempting to compute some two-loop amplitude in QCD, in practice, I mean, this is the route that people go. This is somehow from experience, a very generic and highly successful approach, and integration by parts identities play an important role. And I mean, over the past 2 years or so, I mean, several processes with two partons in the final state, also including cases where you have massive vector bosons, have been computed precisely in this way. Okay, but as I advertised, I mean, so the basic idea in our approach is, again, we want to study these IPP reductions. This forms a large set of these linear relations among loop integrals that we want to use. Again, the other set of linear relations are just the discrete symmetries that we know from standard quantum field theory. But the basic idea is that we're going to be studying these reductions on generalized unitarity cuts. So cut here means simply replacing a propagator by a delta function according to this prescription. So that's unitarity cut, but I'm deliberately using this word generalized unitarity because I'm going to allow myself to apply any possible cuts, to any, pick any subset of the propagators in the problem and allow myself to put those on shell. I I mean, in particular, when I'm talking about cuts, they do not necessarily have to be so that they're, cutting an L loop diagram into a tree in L-1 loop, or I mean that they're computing discontinuities in the various kinematical channels. They don't have to be such. They can be, it can really be any subset of propagators that are being put simultaneously on shell. So this idea we already exploited in our paper from late 2015. I should mention that there's also a paper by Harald Ita that uses some of these ideas. The point of using these cuts is that they dramatically simplify constructing these IBP relations. The point here is that if any integral that appears in the linear relation is missing any one of the propagators in the set S, then it will be put to 0 on the cut. It's basically just because the cut is now computing a residue of a pole, and if there's an integral that's missing any one of the propagators in the set S, the integral is simply missing the pole whose residue we're trying to compute. So it'll be 0. And so that means that by applying these cuts, we can really filter out a lot of integrals. We'll see how this works in practice later, of course. But as the basic idea is then that starting from the maximal cuts and iteratively releasing cut constraints, we can produce all the IBP identities that we need to find the basis of integrals. Okay. Now, so I need to explain a little bit about the setup here before I can explain. So the goal of the next few slides will be sort of to explain how we actually find IBP reductions on these cuts. But this requires me to do a few changes of variables. So to be pedagogical, I decided here to focus on the 2-loop case. The algorithm works also at higher loops. We've tested it successfully at 3 loops, and there's no inherent assumption about 2 loops. I'm just choosing it here because it's the simplest non-trivial case that I can look at. So with that in mind, a general Feynman integral takes the following form. So I'm considering propagators d1 through k here, and some arbitrary numerator insertion here. Some polynomial in the loop momenta. Can also depend on the external momenta here, of course. I'm working in dim-reg, in dimensional regularization. So my momenta are d-dimensional, but I'm going to decompose these d-dimensional loop momenta into a 4-dimensional piece and some extra dimensional piece here. So if you're asking why is 4 dimensions special, that's because our external momenta are 4-dimensional after all. So 4 dimensions are special. And then for this extra dimensional piece here, for these extra dimensional vectors, instead of using these as integration variables, it will be more convenient to use the lengths of these vectors and their relative angles. I'm going to do first this decomposition and then the change of variables from these Li perps into these objects here, these mu's here. And after doing so, our integral will then take this form here. And where this is some extra dimensional gram determinant here, some of you may recognize this object. Okay. Now, since, as I said, we're going to be applying cuts and constructing our integration by parts identities on these cuts, this idea sort of motivates using the following set of variables of our problem. So I will use these integration variables, these zi, which are defined to be inverse propagators so far as they are available. So my diagram has k propagators, and then for the remaining integration variables that cannot be chosen as inverse propagators, I choose objects here which are precisely polynomials in the loop momenta that cannot be written as linear combinations of the inverse propagators. That actually has a name in the literature, is known as irreducible numerator insertions. And a technical remark is, it doesn't matter for the formalism how these are chosen. Of course, the results ultimately will not depend on the choice, but it's going to make your life a lot simpler by choosing the g's to take the form of something that looks like inverse propagators with a prefactor of a half, for technical reasons having to do with canceling the mu's. In this way, you basically avoid introducing spurious square roots, and this map here has a nice polynomial inverse. I mean, as opposed to introducing some spurious branch cuts. And so after applying this change of variable, the two-loop integral that we were looking at now looks like this. And this f here again was just the extra dimensional ground determinant that we had here. The z's here precisely are propagators that we had here.
Sorry, what's the capital K?
Capital
Capital K, J, which you add to the loop. The J equal 1/2 L J plus KJ.
This is just some sum of external momenta. So again, you have to choose. I mean, it's advantageous to choose the g's to take this form, and this is supposed. So capital K just means it's typically some sum of external momenta. Yeah. Okay. I should say there's a slight caveat to this formula. So this is a general formula that works at two loops. This is this caveat that the formula as it stands works if you have at least 5 external particles. The caveat is that if you have, let's say, 4 external particles, then 4 external momenta, then by momentum conservation, only 3 of them will be independent, and that means that there's some orthogonal direction, we call it omega, and as it turns out, the component of the loop momenta along that omega direction can be essentially trivially integrated out in this integral. So that would have the effect of changing this number here down to 9. I mean, having integrated out one component from each loop momentum. So if you have 4 external particles, then this number would be 9. And moreover, integrating out has basically the effect of changing the critical dimensions that you see in this formula, shifting them down by 1. I mean, it's sort of consistent with the fact that the kinematics has 1 dimension less. So, for example, it's going to say d minus 6 here, and then correspondingly for the prefactor. So I say this because the next slide I'm going to be considering that case again, because it's a little bit more manageable to look at 4 particles. So it will be basically this formula, but with this caveat. So, but again, I mean, otherwise this is a completely general representation, and we later learned that Bykov had actually arrived at this representation in a different way, and already back in '96. Okay, so anyway, coming back to what I was saying before, the idea is we want to study these integration by parts identities on cuts, and so let me choose. It's still a non-trivial, but not hopefully too involved example. Just massless Fock-Luan scattering, and let's look at this object here, planar double box. And again, the notation means here these dotted lines. That's again, I mean, the dot product between the adjacent momenta here, and then raised to these respective powers. So so their relation saying that these objects can be written as linear combinations of integrals of this form. And now I want to show. I mean, of course, that there's additional terms here. I mean, there's further integrals. I mean, I remind you that we had a relation like this one, so I'm only highlighting these contributions. There are additional contributions, but these additional contributions are put to 0 on this cut that I'm considering. And for the moment, we don't have to worry about them. So now the question is, can I construct these relations here on this cut? I mean, can I determine these coefficients C1 and C2? So what I'm going to do is first of all to use these ZI variables that I just advertised. So they're going to be the inverse propagators so far as they're available. So I've labeled the propagators in this way. Now, as we saw before, I mean, we had 11 integration variables. Remember, because we had 4 components in each loop, 2 loops, so that's 8, and then we had the 3 mu vectors, the length of each of them and the relative angle. So that's an additional 3. That's why we have 11 here in general. But now, since we're in this special case, we could integrate out 2. We had 9, so 9 z's, and then only 7 propagators. So there's 2 additional z's that I must choose somehow. And again, as advertised, I choose them to sort of look like inverse propagators, but with a prefactor of a half. So this is my choice of variables. And then the thing we want to do is to put all these propagators on shell. And doing so, our double box integral then takes the following form. So we have the standard measure factor. All the propagators have now been replaced by delta functions. And P here refers to some arbitrary numerator insertion. I mean these polynomials here. And since we're restricting ourselves to the solution of the delta functions here, all the z's are put equal to 0. So the effect of applying this cut to this integral is to replace the original integral with this one here, where you have the delta functions. Okay. Okay. So let me now simply integrate out these 7 delta functions. Then I'm left with 2 z's, Z8 and Z9, and the maximally cut integral takes this form here. Okay. So now what we're trying to do is to find these integration by parts identities, which, as I said, they basically arise from acting with total derivatives with respect to the loop momentum inside the integral. So let's try and think about what is now, to get the general linear relation compatible with this form. Let's try and think about what is the most general total derivative, or in other words, exact differential form that I can write down that has this form. I mean, as if where the form now has these 2 variables, and where my P of z again is a polynomial. Well, the answer is simple enough to write down, so that's simply this object here, where my AI of z are a priori at least completely arbitrary polynomials in the z variables. Now, if and this, I mean, never mind really this prefactor here. This is just from, how do you say, permutation reasons, because the wedge product is antisymmetric. So this is not important. It's just here for notational convenience. Anyway, if I write out the action of this exterior differential operator, basically by definition, I have this object here. Now, writing out the action of the differential operator on each term here actually is interesting, because we get 2 terms, and this red term here is interesting, because it actually, at least if you're just choosing generic polynomials AI, then this actually corresponds to an integral in d minus 2 dimensions. So why is that the case? Well, that basically has to do with this f here downstairs. So you notice that if the AIs are just chosen arbitrarily, this f will divide against the measure and basically has the effect of shifting down the space-time dimension here by 2. Now, on the other hand, if we were to choose our AIs in some special way, such that sum over I, AI, df, dzi were proportional to f, okay? Suppose we choose the AI in that way, then we notice that in that way of solving for the AIs, the f would just divide against this, and the measure factor would be left intact, and we would have something that really honestly corresponds to a total derivative in d dimensions. So that's basically the idea of what we then proceed to do. So so this equation is basically just saying what I just explained. So the way we can ensure that this really corresponds to a total derivative in d dimensions is we say this has to be a polynomial, really, rather than a rational function. In other words, that this sum over I, AI, df, dzi has to be proportional to f. Okay. So in other words, if we can find solutions to these kinds of equations, we can simply plug them in and we get our total derivatives. And here I should say that these kinds of equations are well known in algebraic geometry. They're known as syzygy equations. And I mean, if you require that the solutions AI, comma b are polynomials, then you call these syzygy equations. And they've been considered in various contexts in the subject in several papers here. And one of the nice things is also that just because they've been known in algebraic geometry for quite a while. There are also existing algorithms for computing these, and including some more recent ones by Foucher, which are quite efficient. Anyway, the idea is that you write down the syzygy equations that appear in the problem, and you find a generating set of solutions. So Noether's theorem guarantees that there will be a finite set of solutions, at least for the f's that you encounter. They will never, if f is a constant, this theorem doesn't apply, but it will never be constant by construction. So Noether's theorem tells us that there is a finite set of generating solutions to this equation. An important observation is now that once you have a solution to this equation, if you multiply this by some arbitrary polynomial, then this object here will also be a solution. I mean, as I guess is obvious. And in practice, these Q's here will correspond to the irreducible numerator insertions of the problem that you're dealing with. I mean, the powers are then dictated by, if you're looking at gauge theory, there's some upper bound. If you're looking at gravity, this upper bound is somewhat higher. But these Q's have a specific meaning in a given physical theory. Anyways, it's important to remember that if you ask some software to solve this for you, you will get a generating set of solutions, and you have to supplement additional solutions. And we have the full set of solutions. You plug them into this ansatz we have for the total derivatives, and this gives us, by expanding the action of the differential operators, the linear relations that we're interested in. So this is some sketch of how we actually construct these linear relations. Yes.
Which is
In
the
practice.
functional form of f in terms of z in general? Is this algebraic? Or
Oh yeah, so actually it's a polynomial. It's a polynomial.
Polynomial.
Yeah, it's always
Yes.
a polynomial.
That's back to what I was asking. If
Ah.
it can't just be a generic function. Right?
No.
Okay.
Yeah. No, again, I mean, I mean, actually, to be technical, it has something to do also with the way you're choosing, these G's here, because again, the f arose from this object here, and then you have to worry about the mapping from the mu's to. So, but yeah, but okay, we don't have a proof, but I mean, in fairly non-trivial cases, so 5-point scattering with one mass, and several cases, we've been able to find these maps, and it always works. So it's so yeah. I mean, thus far we've always been able to find transformation that renders this f.
In cosmology or large-scale structure, we do some similar loop integrals, but our initial power spectrum f or p is just the thing we get from distribution of. It's just a generic function.
Yeah.
So I was wondering if there's a way to find these similar relations. But
Well,
anyway,
yeah.
yeah.
Okay. I think I should also speed up. Wow, I'm behind here. Okay. Let me proceed now to explain sort of the basic algorithm of what we're doing. So we're given some input diagram, and the idea. I mean, what the output is going to be. I mean, it's given, for example, this double box graph. Consider the vector space spanned by the graph and all of its subgraphs. So this is finite dimension, and the object is to find the basis of this vector space. That's the output of this at the end. The way this works in practice is, you look at the graph, we call it gamma, and all of its subgraphs. And for each subgraph, including the original graph, you find the automorphism group. We then proceed to find a list of cuts on which we're going to construct these IPP identities. And this list, to avoid any redundancy, we choose this list such that there's no two cuts that are related by discrete symmetry of the graph or any of its subgraphs. If there would be, that would mean that basically you're constructing redundant IPP identities. I mean, you've already constructed it on one cut, then there's no need to construct it on a cut, which is now just the image under some discrete symmetry. So that's the reason for this. In practice, when we construct these identities, of course, there are numerical invariants. For example, Mandelstam invariants S and T could be external or internal masses in the problem. There's also the space-time dimension. For the purpose of finding a basis of integrals, there's no need to keep the algebraic dependence of these these invariants around, so we can just choose numerical values. And for technical reasons, it's even what's even better than choosing integers or rational numbers is to choose finite field coefficients. It's a technicality, but anyway, I mean numerical values for all invariants in space-time dimension. And having set up all these linear equations, which at this point will be in this kind of block diagonal form, which I mean, if you may remember from the first slide, we simply apply a Gauss-Jordan elimination to the system of identities, and then the non-pivot columns will precisely correspond to the integrals that we will choose as our basis integrals. So just try and run through these steps. So if we again can consider massless 4-point scattering, there are 7 propagators. A priori, it would seem like we have 2 to the 7 cuts to consider, I mean, on which we have to construct all these integration by parts identities. In practice, there's only 34. And the way you find these is sort of through this chain here. I mean, this is what the code does. I mean, so you start by looking at the original graph, and you notice that it has both an S channel and a T channel symmetry. And if you mod out by these symmetries, you find that there's actually only 48 that are independent. Then the next few graphs that then appear don't give additional symmetries. Once you get to this graph, there's the symmetry. You can flip the 2 propagators here, which gives you some further symmetries, and modding out by those, you're left with 42 cuts, etc. You find that you only need to construct identities on 34 cuts, which I've written here. So these are the cuts that the code then traces through. There's actually a little bit less, so the code gives you a slightly over-complete number of cuts. Some of them turn out to be identical. So there's 29 here, not that it's really important, but anyway, this is the first step. And then, so what we're going to do next is to find linear relations on each of these cuts here in turn. So for example, the first one, I tried to explain how we derive identities on that cut in the previous slide. Let me just give you the result that you find. So again, with this labeling of the internal lines and choosing these values for the external kinematics, I mean, 9001 is a good prime number. That's the reason for choosing this. We have a relation that looks like this. Again, the notation here is referring to powers of numerator insertions. And let's say if we're considering gauge theory, then the relevant integrals that we have to look at for this topology are in this list, which we can record in a matrix, and then we apply Gauss-Jordan elimination to this, and we find that the non-pivot entries are the interesting ones, right? Because, I mean, for example, this entry here tells us that this integral here, which is this one here, can be written as this linear combination, as a linear combination of these 2 entries with these coefficients. In other words, I mean, these are precisely the integrals that we're going to choose as our basis elements. It makes perfect sense. I mean, that of course the non-pivot entries are added to the initial empty set as part of the basis. Then the next step will be to proceed with some of these cuts. I think the next one I'm showing is this one here. As it turns out, in this case, all the linear relations relate powers of insertions into this integral into integrals that are obtained from this by pinching at least one propagator, so that on the cut where you put all the propagators on shell, you actually find a 0. And so for this class of topologies, no elements are added to the basis in this step. And the next step, we consider this cut here. You find that all integrals of this topology with these insertions can be reduced to this integral with this just a 1 appearing in the numerator. And so this integral with a 1 in the numerator is added to the basis. Okay, and so forth. Okay, and then, I mean, there's a few more things that the code does for speed purposes and to avoid redundancy. So it detects if a graph has massless tadpoles. For example, this integral here vanishes because it has a massless tadpole. So these are just removed. Also, at any given stage, it's important not to look at the input momenta. Means on our problem we had P1, 2, 3, 4, out of which by momentum conservation 3 independent. Rather than always treating these input momenta as the external momenta, it's much more advantageous to look at the momenta of a given graph. So for example, here in this case, there's clearly just 3 momenta we should consider, and so by momentum conservation, only 2 of them. And the effect of this technically is to reduce the number of scalar products. When you go to these lower topologies, for example, something like this here, or this dramatically speeds up the code, especially as you go to 3 loops. So this is technically quite important. Okay. Now I'd like to just mention some applications of Azurite. So I couldn't resist this. Okay, so yeah, I can mention that these were not just taken from Google Images. I actually took these pictures myself. So these were from this summer Salzburger Festspiele. You have the this is the fortress of Salzburg, built to be very imposing, and the city was never invaded precisely because it was so imposing. If you visit the royal chambers here, you have to pay a small extra fee. You'll notice that the ceiling here, which is supposed to be a starry night, is precisely coated with Azurite. And the same in Chateau de Blois. This hallway, which is, I think, as I recall it, somewhere here, was used as a judicial court in the 1600s. Anyway, so these are some applications of Azurite. But okay, going back to our Azurite, to give you a taste of something fairly non-trivial, this planar triple box topology. If you input this graph into Azurite, it will give you back 26 integrals of these topologies here. So there isn't quite 26 in this slide. There's 19 integrals. That's because for some of these integrals you need to include the integral, along with possible irreducible numerator insertions to get a full spanning set. So in the paper we explain which ones form a choice, a good choice. And just to give you a little bit broader sample. So these are some examples we've applied the code to, timing and number of master of integrals. You can see that for the 2-loop cases, which are these integrals up to here, the longest running time was for this 5-point case was 6.4 seconds. And then at 3 loops, the longest running time was for this tennis court diagram, a little bit less than 3 minutes. The number of master integrals that are found is ranging here between 8 up to 85. I should explain what this notation means. So these things put on top of lines means that the line has some mass, and the triangle versus square versus filled circle means that they're distinct masses. Yeah, and I mean likewise.
Is this Mathematica?
Yeah, it's Mathematica code was used to draw this, which actually turns out to be, well, for the purposes of presentation, not always so easy. I actually wanted to highlight which ones. Anyway, but yes, it is. And now there is some other software that can give you a set of masters. It's called MINT, it's an abbreviation of master integrals, from 2013. So I just wanted to give you some idea of the relative timing here. So the thing that I want to sort of point to is that as you go to increasingly more complex problems, our code is faster. I mean, at first by a factor of 2, which is not very significant. Then it's like a factor of 5, and then for the tennis court, I can't really report on a number. I mean, basically what happened is we let this run for this amount of time, and then on the computers we had available, the computer just runs out of memory. So if maybe if you set it up on a different, if you had more memory, it would finish. I mean, maybe it was 95% finished. Who knows? But at least I can say that on a desktop computer we could do this in 3 minutes, and so the factor here is something more than 1,000. Okay, and now I'm well on time for my conclusions. So, I mean, as we've heard, I mean, we've developed here is a new algorithm for finding bases of loop integrals, and we've implemented it in a package which is mostly using mathematical functions, but also singular by the name of Azurite. The idea of the algorithm is to construct the needed integration by parts identities on maximal cuts and then release cuts iteratively. And along the way, we use graph theory tools to find the automorphism groups of the graphs and subgraphs. I want to emphasize that the algorithm is completely general, so it works for any loop order, any multiplicity, whether the diagram has internal and external masses, is planar or non-planar. Of course, in practice, we've only tested it up to 3 loops, and I mean, if you give me a graph with 28 loops, I mean, obviously the running time is perhaps going to be prohibitively long. But at least in principle, I mean, there's no assumptions on anything here. It is faster than existing software by a factor that increases rapidly with the complexity of the problem, up to a factor of more than 1,000 certainly. And I should also say that this Azurite provides it really provides also an initial step that was needed for the full problem of finding IPP reductions. I mean, so in this paper here, which is a little bit more than a year old, I mean, we actually gave a formalism for constructing the complete IPP reductions. I mean, here I've only talked about how to find the basis of integrals. There's the question of how you find these reduction coefficients, and in this paper we explain how this can be done. But an ingredient that was missing is again the idea somehow to construct the IPP identities on cuts. But one has to find sort of an appropriate spanning set of cuts, and this is non-trivial. And the needed ingredient for doing that is precisely to find a choice of basis. And so this package fills in that gap, so that actually what we're doing now is precisely to work on this algorithm here, with the hope being that we can actually provide IPP reductions that are not available with current technology, such as FHIR. FHIR is one of these online available IPP solvers, but it gets stuck if you're trying to do, for example, QQ bar to 3 jets, which is needed for LHC phenomenology. To deal with the non-planar sector, this is something that cannot be done with current software, and we're hopeful that we will be able to with the approach of this paper. And then again, I mean, that's where Azurite fills in the gap. All right, thank you for your attention.
More questions?
Okay, there are already quite a few questions. Yeah, I guess it's quite a technical subject as well. Anyway, I hope it was comprehensible. So. Yeah.